Okay, well, welcome back. Today we're talking about conservation of energy. So the thing that you absolutely have to know is energy is neither gained nor lost in any process. So you're probably wondering then, what in the world happens when we have a bouncy ball? So here's the floor, here's the bouncy ball with a v sub naught equals 0. Now it has a height above the floor, so it has a potential energy up here equal to mgh. As this descends, if you let it go, then at this point, position here, there is no h anymore. So it doesn't have any potential energy at this point. This would be 0, this would be max. Okay, and then halfway in between here, potential would be half. Well, what do you think the other half is? Well, kinetic energy then comes into play, because that's what happens. Our potential turns into, as you know, we get a bigger and bigger velocity as we go down, until finally we have realized our full potential just before it hits the deck. And all that potential then is turned into kinetic energy. So this kinetic at the bottom then is max. Well, then what happens is the ball squishes down. So I'm going to show the next step over here, even though it would be, on top. But the ball squishes down. You don't see it that much. But at that point, then the ball is becoming a spring. Okay? So now at this point, there's a potential energy equal to a spring, or potential energy of a spring. We'll talk about that later. But once it gets as flat as it's going to get, all of the kinetic energy that I had here then turned into full potential energy of a spring. And no kinetic, because there's no movement at that point. And so then the next step is the ball unsprings itself. And then at that point, all of the potential of the spring that was there then equals the kinetic energy right here, and the ball takes off again with a V. Now, the question is, why does it not reach as high of a level? Well, there's a couple different answers to that. We hear the ball bounce, and if we hear something, that's sound energy. We see the ball squish down, and so you're moving the particles that the ball are made of into a deformed state. Depending on the ball, you'll lose some energy to heat, which would mean the particles of the ball are actually jiggling and wiggling around more than they were before. And then also the floor is going to be wiggling and jiggling around more than they were before. Okay, so if you look at the next part of the notes, we kind of have another situation like this, and it's got the ball here, where v sub naught equals 0, but it's a pendulum. So there's another position here and another position here. Now, if we do not lose any heat here, like if you hear the child swinging on the playground, you hear the right? That would be loss of energy, and quite a bit of loss of energy. That's why you have to pump when you're on the swing. But in this case, we're going to talk about this not being the case. And so what we would see up here is we have a full potential, okay, and then here we have a full kinetic, and then a full potential, and then if we had this here, we would have half kinetic and half potential, and same here, half potential and half kinetic. So the big idea throughout this situation is mechanical energy is constant. Okay? So mechanical energy is constant, which means I go between kinetic and potential energies, and all I do is change the type of energy. So it's either movement or position. As long as we don't lose any friction, our numbers will be perfect. So in other words, if I have 10 here, then I'd have 5 joules of potential halfway. And when I mean halfway, I'm talking about from here to here. This would be the halfway mark. Okay? So I'd have 5 joules of potential, 5 joules of kinetic. Down here, I'd be 10 joules of kinetic, then I'd have 5 and 5 again, and then 10. And this thing would just keep going all day long if there was no air, no friction. Okay, and a very good pendulum will go all day long. So that's kind of the gist of the conservation of energy. It's pretty simple, but then if we look at the notes, we're going to have to see how we can put some math to this stuff. Okay, so read through the notes, talk about what we talked about, and make sure you read these notes. Okay, so here's a question. A ball has no initial kinetic energy and no final potential energy. Oh, well, that's a... Okay, so we're going to do a quick problem. Let's say that I have a height here of 4 meters and I have an initial velocity of 0. The question is, what is the velocity when it falls? Now, I want you to use the energy formulas. So, my potential energy at the top is going to equal my kinetic at the bottom. Do you agree? So, my potential would be mgh equals 1/2 mv squared. Oh, look at how nice that is. Masses cancel out. My velocity equals the square root of 2gh. Well, that looks really familiar, right? Because isn't that the same thing, the same result as v squared equals v sum naught squared plus 2ax? The difference is this doesn't give you any direction. So when we did this, we were talking about vectors, but this doesn't give a direction. It just gives a final velocity. Okay, so let's look at another one here. Let's say I have an initial velocity of 5 meters per second, and let's say I fall 4 meters, and I'm trying to figure out here now what my velocity is. Okay, so this is a little bit more intricate, because at the top now, I have potential at the top, plus kinetic at the top, and that equals kinetic at the bottom. Okay, so this is different. So we say mgh plus 1/2 mv squared equals 1/2 mv squared. And we can say v sub naught here just to make sure that we don't screw those up. Well, the nice thing is we can still cancel out our masses, right? So then we have gh plus 1/2 v sub naught squared equals 1/2 v squared. Okay, so if you solve for v, then you take the square root of 2gh plus v sub naught squared. Well, that looks just like our other kinematic equation as well. I mean, it's the same kinematic equation that it looks like, right? But the idea here is that you need to make sure that when you do these problems, you separate out the energies at the top, because if you don't, then you will have, you'll mix up your velocities. In other words, what kids have done in the past is they said, well, I have 5 meters per second here, and then they figure out their mgh difference and set that equal to 1/2 mv squared, and then they find a v according to this, and then they just take and add that v to that. That does not work. So you can't just add to your initial velocity. You have to include that velocity in the energy form and then solve for your velocity. Okay, here's another little example for you. Let's say that I have a velocity of 10 meters per second, and I'm trying to figure out how high I go. Okay, so what's my h? So I know that up here, I'm going to have 0 meters per second, right? So I'm going to have full potential, and kinetic is going to equal 0. So this time my kinetic at the bottom equals my potential at the top. My 1/2 mv squared equals mgh, cancel. My h then equals 1/2 v squared over little g. See how easy that is? So you plug and chug and you find out 5 meters is the answer. Okay, so that's a little bit easier than the kinematic equation. But just remember, this doesn't give us direction. Okay? A couple more examples. Let's say that you built a roller coaster that goes like this. Okay? And let's say that this height here is 10. This height here is 5. And let's say that my V sub naught up here is 0. But the question is, how fast will it be going at this point, as long as it's a completely conservative roller coaster? Well, your kinetic energy is going to be equal to your change of potential. So 1/2 mv squared equals mg. And then the h is not 10 or 5, but it's 10 minus 5. So I guess it is 5. You cancel out your m's, and you get 1/2 v squared equals 5g. And so my v then is going to be the square root of 10g, or my velocity is going to be 10 meters per second. Okay, now it's not down, but it's directed in that direction because of the roller coaster. Okay, so it's actually the same number that you would get if it fell straight down, but this energy thing doesn't have direction. So it's kind of nice because we can figure some things out this way. Okay, so then another idea that we have here is, let's say that we have something that's a height of 10 meters, and we have a ball that is going to have no rotational inertia. It's just going to roll on down, complete conservation of energy. The question is, what's the velocity down here, right? Well, before you'd have to figure out the force that's directed down the ramp, right? Or you'd have to figure out the acceleration that's directed down the ramp. But if you understand this kinetic energy thing, then really all that's happened is I've had a change in height equal to 10 meters. So again, you just go, 1/2 mv squared is equal to mgh. So my velocity then equals the square root of 2gh. And I can figure out my velocity here. So it's much easier to do. You don't have to do any trigonometry or anything like that. You might have an angle, but you don't need an angle. Now the difference between this velocity being, 7 or 8 or whatever it is, if I dropped it straight down, it wouldn't take as much time as it does going at an angle. So it takes more time, but still the answer is really equal to the change in positional energy, and that all turns into kinetic, unless we lose some in friction, which we'll talk about later. Okay, hopefully that helps for the next 2 worksheets.